We will now be starting chapter 3, which is all about limits. Please note that our main text has a very quick introduction to limits, so I wanted to make a very thorough explanations and have lots of examples, so we will be using a supplemental text for this particular chapter, which is why in the notes it's called chapter 3a. So look at the blackboard for the supplementary textbook. Today we will talk about just the introduction to limits, informal definitions, and some very basic notation and calculations. So this is what I call a very informal definition of a limit. It essentially comes from the word limit itself. In real life, when we hear the word limit, we associate it with something that one approaches, something that is kind of like attained as something, right? So for example, a speed limit. It's something you want to come as close to as possible. So if the speed limit on the road is 50 kilometers an hour, you don't want to be driving 35, and you also don't want to be driving 75. You want to be as close to 50 as possible. You could be driving 48, or you could be driving 52, and sometimes your actual odometer won't be able to tell you with that much precision what you're driving, what your actual speed is, but you want to be as close to the limit as possible. And that motivates exactly what a mathematical limit is. So the very informal definition is that the limit of the function is the y value that it approaches as x approaches some specific value. So an x value will be specified for you, and you will have to calculate the y value that the function approaches as x gets closer and closer to the pre-specified point. Let's take a look at our very first example here. Find the limit of a function y equals x squared as x approaches 2. So we're given the value that x will approach, it's 2. Let's mark it here on the graph, for example. So this is the value of x that I'm going to try to stay close to. Finding the limit means I have to find that as x is around 2 or as close to 2 as possible, what does the corresponding y value on the graph approach? Right? This is a nice simple function, so the answer here is pretty clear just from the graph itself. If x is really, really close to 2, then I expect that my y value is going to be really, really close to 4. That's how one can justify it from the graph, but we don't always have graph readily available. Let's think about what would we do if we had to plug in numbers. Now, I must warn you that plugging in numbers will give you great intuition about some limits, but it will fail miserably sometimes. So while you can do that, this is by no means a foolproof approach, which is why we're going to spend quite a bit of time talking about analytic and formulaic techniques to actually calculate limits in a much more precise ways. Before we start plugging in numbers, we have to wonder what kind of numbers are we going to plug in. So as x approaches 2, what does that really mean? So x has to be close to 2. Does it have to be close to 2 and less than 2? Or does it have to be close to 2 and bigger than 2? This doesn't specify that, so we actually have to consider both cases. So let's plug in some numbers here. So my table here will specify the x values that are closer and closer to 2 but less than 2, and that are closer and closer to 2 but are bigger than 2. These are the x values that approach 2. How do we calculate the y values that correspond to those? Well, our function is given here, y is x squared, which means that to find the corresponding y value here, I just have to take the corresponding x value and square it. Okay, you can try it for yourself on a calculator, but I have the table filled out here for us. So when x is 1.9, y is 3.61. When x is 0.199, so even closer to 2, y is 3.96. When x is even closer to 2, 1.999, y value is 3.97. Okay, so of course you can continue doing this for a while. Same on the other side, but we can clearly see the trend, and that is that as x's approach 2, y approaches 4. Now there are two cases that we're seeing here, right? So once again, it can approach but be less than 2, or it can approach but be bigger than 2. And those are actually two cases that we will distinguish. So this, we will say x approaches 2 from the left, because it's physically on the left of the number line. In this other case, we will say that x approaches 2 from the right. Okay, and again, it's easy to see on the graph what that really means. If this is my 2 right here, then approaching from the right means that my x values are close to 2 but bigger than 2. Approaching from the left means my x values are close to 2, but less than 2. Now, because mathematicians are lazy and we're going to do this approaching from left or right a lot, instead of saying approaching, I'm actually going to use the arrows. So the mathematical notation for x approaches 2 from the left is x goes to, arrow, 2, and then to say that it's from the left, I'm going to use a little minus in where the power would normally be. Similarly, x approaches 2 from the right will have a little plus, signifying that it's close to 2, but a little bit bigger than 2. Okay, so we can say here that the limit as x approaches 2 from left or right seems to be going toward 4. Now let's take a look at not very informal, but just informal definition of a limit that will also introduce a very useful notation that we can use for the limit in order to save us from always writing as x approaches 2 the limit is, and so on. So my function here is f of x. The number x is approaching is a, and L is the limit itself. The notation, this notation, limit, we read it as this, limit as x approaches a of f of x is equal to L. So the word limit is on the outside, the function is the one that we're using. This specifies what the x value is, and this specifies what the corresponding y value is of the corresponding limit. So going back here, just for practice, on the left here, we had that the limit then as x approaches 2 from the left of our function, which was, again, remember, y equals x squared. So of x squared is equal, we decided that it was in fact approaching 4. And similarly, on the right, we can say that the limit as x approaches 2 from the right of our function was also equal to 4. Okay, so this is just how we use the notation. Now, this very informal definition is also useful in the sense that we can justify what some limits are going to be. If the function is somewhat nice, what it means to be nice, we're going to get to in a little bit. But this describes what the real meaning of the limit is. It means that the values of f of x can be made as close to the limit value as you want, by taking x sufficiently close to the chosen value. So for example here, I can make the y value be as close as I want to 4 by taking x's to be as close as needed to 2. Okay, let's see if we can, without graphing anything, if we can justify ourselves what a given limit would be. So here the limit is, as x goes to 0, of 2 to the power x plus 3. Okay, let me rewrite this just in a bigger font. So we read this as limit as x goes to 0 of 2 to the power x plus 3. I'm going to write it slightly bigger because I'm going to draw arrows and things like that around it. Okay, so the limit specifies that x goes to 0. But I don't know what this function goes to, and that's exactly what the question is asking me. But as x goes to 0, I can denote this a little bit here, right? This x goes to 0, which means that x is going to be really, really close to 0. It could be a really, really small negative number, or it could be a really, really small positive number, but no matter what, it's going to be really, really close to 0. If you would like, pause the video here and plug in some values into this function where x is really close to 0, just again to see intuitively what the limit would approach. Now, if x is really, really close to 0, so I'm taking a very small positive or negative number, then what does x plus 3 approach? So this whole thing. If I'm adding a very small number to 3, then the sum will be very close to 3. Okay? And then what I have overall then is that I have 2 to the power that is really, really close to 3. So overall, I'm going to have 2 to the power 3 in the limit, which is, of course, 8. Okay, so this is the way that you can justify it out. Again, functions have to be nice and create no problems like division by 0 and things like this. We will learn how to deal with those shortly. But if you're just sort of plugging in your head or justifying what happens as x approaches a certain value, then you can intuitively understand what the limit value will be as well. Now, this is an informal definition, and this, in fact, is the definition that we will mostly work with. This definition, in many ways, is the original non-rigorous definition, because that was the definition that was used by Leibniz and Newton when they invented calculus in the 1800s, in the 1700s. So those ultimate ratios are not actually ratios of ultimate quantities, but limits which they can approach so closely that their difference is less than any given quantity. So it's talking about how you can approach something infinitely closely. Now, this non-rigorous definition was not actually enough for development of some mathematics and particularly concepts in physics and things like elasticity. So over 100 years later, Cauchy, Weierstrass, and Bolzano came up with a much more mathematically rigorous way to specify what limits are. This is not a definition that we will work with, but I wanted to show it to you anyways and to show on the graph what it actually means, because graphically it's really easy to understand. I should also point out that if you have a minute, you really should look up some of the lives and biographies of these incredible men. So Cauchy was a French mathematician. He's in fact one of the 72 names that are inscribed on the Eiffel Tower as the biggest French contributors to science. Weierstrass is a German mathematician. One of the interesting things about him is that he was a great supporter and mentor of the first female mathematician PhD, which was Sofia Kovalevskaya. And Bolzano was an Italian mathematician. He's also a very interesting figure. As opposed to Cauchy, who was known to be a terrible lecturer, Bolzano was actually ridiculously popular with students to the point where he started lecturing in disciplines that were not his own. And he held very controversial views at the time that money should not be spent on warfare, but rather the government should spend more and more money on education and social systems, which those controversial views eventually cost him his job at the university. And we can see that some countries still struggle with being able to divert some money from warfare to education. Now, let's go back to the limit definition to see what this actually says. So it's easiest to understand graphically. So if I have a little graph here of some function, I'm not going to give you the actual function. I'm not interested in the definition itself. What this is saying is, if I have this a, some value for x that I'm trying to approach, and my eventual limit, so let's say this function is nice and smooth, so my eventual limit is here. What this is saying is we can play the following game. You can tell me how close you want to be to L, and I will tell you where you have to start on the x-axis to be able to get that close to L. Okay, that's all this very complicated looking and very notation heavy definition is saying. This is very useful for things like if your x-axis, for example, is time and your y-axis is, for example, some kind of amount of medication in your system, then you can think of when do you have to re-administer a medication dose. You know how much drug in the system of a patient you'd like to have when you want to re-administer, and then the x-axis will tell you when when a new dose has to actually be administered, right? So again, you tell me how close you want to be to L, and I will tell you which x values will land you there. That's all that the actual definition of limit says.
Now, because this is actually better understood with an example, let's take one. And it's going to be the same context of time versus some amount of drug in the system. In this case, it's going to be morphine. We will assume that the amount of morphine in patient's body, of course, decreases with time as the liver breaks it down and is modeled by this function. Now, this doesn't come from nowhere. This is actually somewhat realistic in terms of the half-life of the morphine as well as other bodily processes. So this is fairly close to reality. What we know, too, is that our patient needs a new dose when the level of morphine comes to within 0.4 of 5 units. So already here we can think about what that actually means. Within 0.4 of 5 units means I need to be between 4.6, which is within 0.4 units of 5 in the smaller side, and 5.4, because that will be within 0.4 units on the other side of 5. Anywhere in between, and I know that I need to re-administer the dose. We are asked to find the window of time when we should actually be administering that new dose. So what I have on the graph here is the graph of this function. My x-axis here is time, and my y-axis here is the milligrams of morphine in patient's body. Now I need to be within here, and that is of course in milligrams, so these are my values for where I need to be on the function in terms of the y-axis. So if this is 5 right here, I need to be within 4.6, so somewhere from here, and 5.4. So up here, right? So I need to be within this window in order to re-administer the dose so that the patient is still comfortable. So if I trace both of these back to my function, I can then take the points, the corresponding points on the function, and go down to my x-axis, which represents time. This will tell me at which point in time after the last dose, which is 0, will the level of morphine in patient's body be at 5.4. I can do the exact same with 4.6. I can go up to the function and then go down to the time axis to determine what time the morphine level will be at 4.6. Notice here that because the morphine level is decreasing, the smaller amount of morphine will be present in the body for the larger value of time, right? The smaller 4.6 here corresponds to the later point in time as opposed to 5.4 that corresponds to the earlier point of time. The morphine actually decomposes in the body, so the further away you move from the previous dose, the less and less in the body you're going to have. Now, while the graph is nice, it doesn't give us the precise numbers for the actual time. In order to determine the exact answer, not just an approximate one that the graph will give us, we actually need to solve this equation to be within these two particular values. So the graph will help us approximate, but solving algebraically will give us the exact value. Let's write that down because this is an important thing. A lot of times, graphs are very useful, but they're never precisely accurate. When it comes to administering drugs to people, we certainly want to be sure. So the graph will show approximate values, and of course, the graph can confirm what your algebraic solution will be, but you still need to actually solve this algebraically. Algebraic solution will be exact. So what do we want for the algebraic solution? What we want is the amount of morphine, which is m of t, to be, as we decided, between 4.6 and 5.4. So we need this value to be bounded by the inequality on both sides, between the smaller value and the larger one. I can then replace this m of t with its corresponding formula. So what I actually want is 36 divided by 2.4 plus 1.7t, and I want this fraction to be between 5.4 and 4.6. Now, this is a pretty straightforward inequality now, except for the fact that there's two of them, but you can solve the one on the left first, and then you can solve the one on the right next, and you should get your solution that t is in fact between 2.5 and 3.2. Now, I'm not going to go over the actual solution to the inequality. This is a fairly standard pre-calculus technique. Take a look at the pre-calculus refresher package in order to refresh yourselves on how to deal with inequalities. But the idea here is that this formula has t in it, and we would like to actually solve for this variable t because it stands for time. And instead of giving us bounds on the amount of morphine, we now have ourselves bounds on the time when we have to administer the new dose. We can also see that our graph was actually pretty good in terms of approximation, right? So algebraically, now I can sign what these values should be. Not that I couldn't really say, although it fell on what seemed like 2.5, I couldn't really write down 2.5 because, drawing lines here was not a perfect solution. But now I know that this is going to be 2.5 and 3.2. You can already see that my 3.2 isn't as good of a graph as my 2.5 was, and that is why, once again, approximating from the graph is only an approximation, not an exact answer. So the conclusion to this problem is that the new dose needs to be administered between 2.5 and 3.2 hours after the initial dose.
The two important nuances about limits that we will have to think about throughout this entire chapter, here's two of them. First of all, limit describes what happens near a point, not at a point. Okay, so as x approaches 2, I'm interested in what happens around 2, not at 2. And this is very, very important, because let's draw a little graph where things go very wrong at 2, but everything looks good around 2. So let's say I have this graph. Everything is nice and smooth outside of this one point. Let's say this is 2, and let's say this value is, I don't know, 3. Okay, so the graph itself is a nice smooth function, except at 2 we have a hole. But again, if I were to compute the limit as x approaches 2 of this function, let's call it f of x, then I will be thinking, as my x's go closer and closer to 2, what do my y values approach? So you can follow this on the graph. As your graph gets closer and closer to 2, what does the y value that it approach? It doesn't actually have to equal to that value. It just has to equal it in the limit, so as it approaches it. So here we can see that it will approach 3, although it will never get to 3. And that's okay. But also notice, for example, that f of 2 here does not exist, right? There's a hole there, so the graph itself doesn't exist, but the limit value does. And the second nuance here is that for the limit to exist, the function cannot approach 2 different things. If the limit exists, it has to be unique. Okay, so let's draw a little graph here as well to justify this to ourselves. So here, what would the function look like if it were to approach 2 different values near, once again, let's say our favorite chosen number is 2. So if it were to approach something one thing on the right and a different thing on the left, so let's say my function looks like this. Okay, so then let's say this number is 3, I don't know, this number is 5. Okay, so then we can see that the limit as x approaches 2 from the left of my, let's call this not f, let's call this g, of g of x, and the limit as x approaches 2 from the right of g of x are going to be 2 different numbers. And again, think about walking along the graph. So as x approaches 2 from the left, it physically means from the left of 2. So as I am walking along the graph from the left of 2, what y value is it approaching? Well, it's approaching 3 here, right? So this limit is equal to 3. As I'm approaching 2 from the right, I'm going to walk along my graph toward 2 from the right. What y value am I approaching? 5. Okay? And this is exactly the problem. If a limit at 2 is going to exist, it cannot be 3 or 5. If it exists, it has to be a unique number. If I'm getting 2 different numbers on 2 different approaches, that means that the limit at 2 does not exist. Okay? Limit as x goes to 2 of my function g of x does not exist. Okay? We're going to see more examples of this graphically, but these are essentially the things that you have to keep in mind going forward with limits. Let's take a look at how one would compute limits from a graph when you don't have a function formula, right? So a couple of examples ago, I had that y equals x squared was our function, but here all I have is a graph. Okay, I'm not going to try to come up with an equation. I'm just going to use graphical representation to come up with limits. Okay, so here though, we're asked to compute function values and also limit values in order to see what are the possible differences. Okay, so first, g of minus 2. In fact, first, I would really like you to pause the video and try this for yourself. Okay, so pause right now and be back when I explain the answers. Excellent. I trust that you're actually good students and you've paused it. Try it for yourself. Math is not a spectator sport. You really should be working this out for yourself as well. So g of minus 2, I'm plugging in minus 2. There's my function g. So g of minus 2 is equal to 0. Now let's compute the corresponding limit here too. So limit as x goes to minus 2 of my function. So as x approaches negative 2 on the left and on the right, again, I'm going to walk along the graph, and I'm going to see that both of those points approach 0. Excellent. The next one, g of 0. Well, 0 is over here. Actually, I'm going to label this here. Okay, so g of 0, I'm going to go up on x equals 0 and look for where the function is, or where does it exist. And it exists right here. This is the filled in dot, right? This is a hole. So my g of 0 is actually equal to 1. That's where the function at 0 is computed. What about the limit as x approaches 0? Again, remember from the last slide, it doesn't matter what happens at 0. As far as the limit is concerned, it matters what happens around 0. So as x approaches 0 from the left and from the right, I'm going to follow the function from the left and from the right of 0 and see that in this case, it approaches 4. Right? It approaches this y value up here, which is in fact 4. Okay, what about g of 1? G of 1, so again, I'm going to think about where can I find the function at x equals 1, and the filled in circle is here, so g of 1 is 3. What about limit as x approaches 1 of g of x? So not at 1, but near 1. And I'm going to go from the left and from the right, and here I see that from the left, it approaches one value, and from the right, it approaches a different value. Okay? So limit here as x approaches 1 from the left is equal to 3, and limit as x approaches 1 from the right is equal to 2. Again, from the last slide, if they're not the same, the limit at 1 doesn't exist, because you cannot choose, right? You cannot choose whether it approaches from the left or from the right. If the limit states that it approaches that approaches 1, and you cannot pick between 2 and 3, that means that the overall limit does not exist. Okay? And last example here, g of 2. So 2 here, there's a hole here and nothing else, which means that there's no value for g at 2. So this does not exist. Whereas the limit as x approaches 2, again, walking toward 2 from the left and from the right, we can see that the y value approaches 1. This is a very important slide here because it shows you that all things are possible. So look, in the first one, the function is 0 and the limit is 0. So the function value and the limit value could be the same. The next one, the function value is 1, but the limit is 4, which means that they could be different. The next one is the function value is 3, but the limit doesn't exist at all. And then the final one, the function value doesn't exist, but the limit does, which means all possibilities are in fact possible, right? All combinations can actually occur. So just because you know a value of a function at a point does not mean that the limit value is the same. It doesn't even mean that it exists, okay? So be very careful. If you're asked to compute it, you actually have to compute each and every case. Now let's talk a little bit more about things that do not exist. Okay, so in particular limits, what can possibly go wrong and when can the limit not exist? We've already seen one important case, and that is the limit does not exist if the left and the right limits are not the same. Okay, so this is going to be our very first case. That's actually, I don't have to number them. It's not like they are in any particular order. So let's say I have a function here. Again, I'm not going to actually talk about a particular function. I just want a representation. So there, the left-hand side limit is not equal to the right-hand side limit. Okay, so limit from the left is not equal to limit from the right, which means that limit at that point does not exist. Let's call this point A. Okay, so limit as x approaches A of some function does not exist, right? And we're describing those cases. Okay, so this we also sometimes call finite jump, because that's what your function does. It jumps from one point to the next immediate. If there's a finite jump, we can talk about an infinite jump as well. So this is the second case. And the infinite jump would usually be in the form of some kind of asymptote. We will discuss asymptotes in much more detail next time and actually describe them in terms of limits. But for now, we can say that this is an infinite jump, and therefore the limit here, jump, also does not exist, right? Because as you approach this value, let's say this is my A now, as you approach this value, closer and closer and closer, the function just keeps running toward infinity away from you and will never be any particular y value. Same as if the asymptotes were pointing toward negative side, okay? And the last case, this case is in some sense the most fun, but also the case we're not actually going to spend that much time talking about whatsoever, and that's the oscillating case. Okay, so here, we're not going to spend too much time talking about this because this is calculus for life sciences, and while a bunch of physical applications actually do have oscillating functions, these types of oscillating functions don't really occur in a lot of naturally described phenomenon like growth rates or anything like that. But they are interesting to look at. The idea here is that no matter how close I zoom in, the function will always be oscillating. It will never have any particular value. So we can take a quick look here at the graph, for example, of this function. It's a cosine, right? Whoops. So I can try to zoom in, but the more I zoom in, I can see that no matter how closely I zoom in, it still goes up and down. So if I fix a very particular point of x, I cannot get close enough to it and have my function stabilize. Okay? But these are the three non-existence cases that we will talk about, and we will start dealing with limits a little bit more algebraically as well.
Let's now explore these situations in a little bit more detail using numerical and graphical examples. So first up, we're asked to numerically evaluate this function, x minus 2 divided by x squared minus 4, to find its limit as x approaches 2. Numerically evaluate means we're going to do the thing that we did at the very beginning of this lecture, which is just plug in various numbers close to the one that we're interested in, and then judge for ourselves, sort of estimate from the numbers that we're seeing what we believe the limit is going to be. Now, before we do that, let's take a look at the function itself. So I noticed that these two terms on the top and the bottom actually have something in common. In fact, I know that I can factor out the bottom and cancel a part of it with the top. The bottom is a difference of squares, so the bottom can actually be factored as x minus 2 times x plus 2. And then, of course, I noticed that this will cancel out the factor of x minus 2 on top, leaving me with 1. Don't forget that just because you cancel the entire top doesn't mean that it's now 0. There's a factor of 1 present there at all times, divided by x plus 2. So what that means is that our function is actually the same as this simpler looking one, except there is one very important difference. So I can say that the function x minus 2 divided by x squared minus 4 is the same as my new function 1 over x plus 2, except at one very important point. And what is that? Let's take a look. If I am looking at this function right here, x minus 2 divided by x squared minus 4, what is the domain of this function? What are the numbers that I am allowed to plug in order to calculate their corresponding y-coordinate? Well, I cannot plug in anything that will give me 0 in the denominator, which means that the domain of this particular function is all x's that are not the roots of the polynomial on the bottom. So x here cannot be 2 because 2 squared minus 4 is 0, which will render denominator to be 0. And x also cannot be minus 2 because minus 2 squared minus 4 will also give me 0. So x cannot be 2 and it cannot be minus 2. For this simplified version of this function, what happened is I have canceled out a factor that will equal to 0 when x is equal to 2. So in my simplification, I have now no longer see the fact that my original function cannot have 2 in its domain. Just looking at this function directly, all I can see is that x cannot be equal to negative 2, because in this new version, all that creates a problem is minus 2. So I've somehow lost information about 2 not being able to be in the domain. So I have to be very clear about it. This function is the same as this simplified version, except x cannot be equal to 2. Okay, so that my domain between these two stays exactly the same, and it excludes both 2 and negative 2. Okay, if you want to draw this, you will notice that what you actually have is like a little hyperbola, something that looks like this. And because it cannot be 2 and minus 2, I will have holes on either branch of the hyperbola here. Now, We are asked to numerically evaluate this function. So I can pull numbers close to 2 and start plugging them into here. So let's say I would like to plug in 1.9 and maybe 1.99, 1.999, and so on. But it's going to be annoying doing so by hand. So here we go. Here's my Google Sheets document. I've already entered, as you can see on the bottom of the screen, the formula for it. And I'm interested in the values of 1.9 getting closer and closer to 2 on the left-hand side, and then 2.1 getting closer and closer to 2 on the right-hand side. So again, depending on the software you use, you might have different ways of extending the formula. I can actually just copy the cell that has the original formula, and then as we go forward, I will simply paste out the same formula, and it will actually adjust to the corresponding entry onto the next line. So here, if I keep going, I see that I'm getting closer and closer and closer to 0.25. In fact, it looks like I'm gaining sort of 1, 0 after 2.5 with every single 0.999 that I am approaching 2 with. Let's see if that kind of pattern repeats on the right-hand side. So I'm going to start with 2.1. Now here I'm starting with 0.24, so I'm starting a little bit less than a quarter, and then I'm getting closer to a quarter and closer to a quarter and closer to a quarter. So here I'm sort of acquiring more 9s after the 0.24, and just looking at these numbers, I can make a somewhat educated guess that the limit at 2 is actually going to be equal to 0.25. One thing to notice here is that when you plug in numbers, make sure you plug in numbers from both the left and the right-hand side of the one that you're interested in, just so you really get a full picture of what's happening on the other side. But again, it looks like coming from either direction, the limit approaches 2.25. So numerically, we can conclude that we believe, or it appears, or something like that, we cannot say it with certainty, that my y value here for this function approaches 0.25 as x approaches 2. Let's take a look at another example that is exactly the same, numerically evaluating the function at a certain point, but the function is going to be a little bit more complicated. So here I already have a limit notation. I would like to know what happens as x approaches 0 to this function right here. Now, just looking at the function directly, I can see that 0 will be a problematic spot because that's where the denominator is going to be 0. So I have to really be thinking about the fact that limits are what happens when x is close to 0, but never actually equal to 0. I cannot plug in an exact value of 0 into this expression, but the limit allows me to plug in something infinitely close to it. And again, I should be thinking about the left and the right. So once again, I don't want to be computing this by hand. Let's pull on the technology and open up the Google Sheets. So as before, I have already entered the formula, and the numbers that I am looking at in terms of x's start from something within 1 decimal place away from 0 and get to be very, very close to it, within 8 or so decimal places to it, right? So if I click on this cell, you can see at the bottom of the screen that it has the right formula, square root of 1 plus this value for x squared minus 1 all over the value of x squared. So I copied the formula into my clipboard, and then I can just actually copy it out. So as I go along, well, this is looking good, right? It looks like it's approaching 0.5. And in fact, here we go, 0.5, but it jumped over 0.5, and now it starts increasing. So this is a little confusing because I'm getting closer and closer to 0. Shouldn't I be getting closer and closer to 0.5 if this is my eventual value? And at this spot is when it starts getting really confusing, because all of a sudden I'm back down to below 0.5, and now we are in real trouble. It is apparently identically equal to 0. Let's see what happens if I plug in negative values that are close to 0. So I start within 1 decimal point there, 0.49, okay. Getting closer to 0.5, getting very close to 2.5, getting indeed extremely close to 0.5, but again, jumped over 0.5 and is now increasing away from it. And now we're back down to some other number. Notice that, of course, my two sides are symmetric because there's squares all over in the formula everywhere. Now I'm back down to 0 values, which is just a very odd thing. But what this tells us is how close you choose is really going to guide your numerical evaluations of the limit. How close is close enough when we're talking about being infinitely close? Clearly, 1 decimal place was not close enough to give us a full story of what happens with this limit. And in fact, even something like 6 decimal places wasn't really close enough, because only after a certain number we started getting identical zeros, which sort of came out of nowhere as well, right? So you have to be really careful about numerically exploring limits, because if you've stopped plugging in numbers at 5 decimal places here, which I would say normally is a reasonable thing that a human might decide is close enough, you would have missed out on how this limit actually misbehaves. So numerically, we noticed that something was off with this limit, but we also have graphing technology at our disposal. So let's graph this function and see if we can confirm our suspicions that something really out of whack is happening around 0. So here's my function here. You see it on the left, 1 plus x squared under the square root minus 1 over x squared. And this is what the Desmos will produce at first. Now notice, of course, we've discussed this before, I don't get to pick my axis by myself at the beginning. It gives me something by default. And so you really have to be mindful of the fact that the default might not be good enough for any particular example. So we are interested in what's happening around 0. So let's start zooming in and around 0. And in fact, I know that I have to zoom in really, really close, because in my numerical explorations, it wasn't up until the 6th decimal place that trouble started really being noticeable. So notice for now I'm between 0.5 and negative 0.5. That's not close enough. So I have to really keep going closer and closer and closer. And this now, within 2 decimal places, I already see that something starts happening. There is now a vertical line on the x-axis. Maybe if I actually make this play a little bit thicker, you will see it better, right? So what is going on here? Let's zoom in a little bit more. And now I'm really getting to see the trouble that this function really is around 0. It oscillates up and down around 0, but it only starts doing so, as you notice at the bottom of the screen, in terms of scale, for very, very small values, for 10 to the minus 4th and so on, right? And now no matter how close I zoom in, I will not actually be able to see anything like that. It oscillates up and down so densely that it now looks like a solid little star. Okay, so if you decide to draw something, also be mindful of the fact that you need to scale up or down to see your graph and its properties properly. So to summarize, 2 important points here. First of all, limits indicate what happens close to the value of interest, not at the value of interest, which is why we're able to actually plug in numbers into the function that would otherwise not be defined at that point. And the second one is taking close enough values might not be good enough, because this is still just a numerical approximation. So while sometimes plugging numbers in is good for intuition, it might not be good enough to actually find the correct answer. Let's now take a look at some graphical limits. Whenever we're computing limits from the graphs that are given to us, we will assume that the graphs actually behave as expected, and the zooming into the graph will not produce some odd oscillating behavior like the one we just saw in the previous example. Okay, so if the function is given to us by a graph, we're assuming that it is well behaved, and we're going to be in fact able to find all of the values that we're asked to find. So here's my graph of the function, and I'm asked to find some function values as well as some limit values. I strongly encourage you to pause the video right here and try this for yourself. You should have all the tools already at your disposal to actually do this on your own or with a friend without having to have me walk you through it. For extra practice and to really solidify the material, try for yourself first. Okay, so let's start out with the function values. We're asked to find the function value at 0. So x is 0, which means I'm here and I'm going up to the function at 0 only to find a hole there. A hole means that there is no function value at that point, so f of 0 does not exist. What about f of 1? If I go through the same exact process at 1, x is 1, I go up and down the function, there's holes here, but I do find a filled in point right there. So f of 1 is actually going to exist and is going to be equal to 2. This point right here is actually defined at x equals 1 and y equals 2. F of 0.9. So I'm going to be a little bit off to the left from 1, and I can see that my function does exist there and is equal to this value. Now, because I'm approximating from the graph, obviously my answer isn't going to be exact, so I'm going to approximate this to be approximately 0.9. Your approximation might have been different than mine. 1.1, I'm up here, so I'm going to look at this here, and again, this is just an approximation, so I'm going to approximate it as 0.1. Okay, so again, just an approximation, and yours might be different, but it gives us some idea about what actually happens near 1. And that is the next question. What about the limit of this function as x approaches 1 from the right? So 1 from the right means I'm going to move toward 1 from the positive side. So as I move along the function toward 1 from the right, what are the y values that I'm approaching? Well, it can be very clear that I'm approaching this hole right here. And again, remember, the limit means it doesn't have to be at 1. It is what it approaches as x approaches 1. So we can see here that it approaches 0, this value, right? It approaches this value right here. So this limit is going to be equal to 0. As x approaches 1 from the left, I'm going to move toward 1 from the left-hand side, but I'm going to do so according to my graph. So I'm going to follow the graph in the direction of x approaching 1 from the left. And I can see that, again, I'm approaching this hole right here, which happens to be at x value of -1. So my limit is going to be equal to -1. Okay? So what we have here is that the limit as x approaches 1 from the right is a value equal to 0. A limit as x approaches 1 from the left is a value, it's equal to -1. But the function itself at 1 is equal to 2, right? So any kind of combination of things can happen. Here, the limit from the left is not equal to the limit from the right, and they're neither of them equal to the function value. And that's totally fine. Our function is just that interesting. Now, the next question is asking to find the limit at 1. Well, in order to find limit at 1, I really should be looking at the limit as x approaches 1 from the left and from the right. And I already found those. And remember that because they are not equal, the actual limit at 1 does not exist. In order for a limit to exist, both left and right-sided limit actually have to be identical values, right? There is, looking at the graph, I can see that as x approaches 1, it approaches to two different numbers. There's a big gap in the middle, so I really can't say anything about what the function looks like near 1 without more information, like whether it's 1 from the right or 1 from the left. What about limit as x approaches 2? So we're looking at it right here. Well, as x approaches 2 from the left, my function approaches this height, or 1. As x approaches 2 from the right, my function still approaches this height of 1. So the limit as x approaches 2 is in fact going to be equal to 1. Now the next two questions are a little bit more complicated. Here I actually don't have f of x, I have f of something, and the limit has to be sort of put into that something first. So if x approaches 0, I have to think about what the inside of my function f here actually approaches. If x approaches 0, x squared will approach 0 from the right. And that is a very important nuance here. Notice that it doesn't say whether x approaches 0 from the left or from the right. But no matter what, this is going to be a teeny, teeny, tiny number, negative or positive. but it's going to get squared. So whether it was negative or it was positive, it's going to come out being positive. So I know that this approaches 0 from the right-hand side. It's going to be a very, very small but positive number. So now I am taking a 2 and adding it to that number. So what I'm going to get as a result of this sum is going to be a number that is very, very close to 2, but on the right-hand side. I'm adding a small positive number to 2, so I'm going to get a number that is very close to 2, but bigger than 2. And now look, I'm interested in what is the limit of my function f as the inside of it approaches 2 from the right. Okay, so in other words, I can actually rewrite this limit as x approaches 2 from the right of just my function f of x. And that is easy enough to calculate. I have 2, I'm approaching from the right, I have to follow the function, and I notice that I end up at height 1. Okay, similarly, the next example is going to be in the same exact vein. In fact, to make it a little bit more complicated, maybe let's turn this into a negative, and I encourage you to work out the actual arithmetic for yourself. Your answer, I'm going to skip the steps here to really make sure that you try this for yourself, should turn out to be -1. Next up, which of the limits does not exist? So we have seen where the 3 situations where limit will not exist. It's things like jumps, so the left and the right-hand side limit are not equal. There's infinite jumps, so asymptotes, which are of course not present on this graph at all. And there's things like oscillations that I already said that if we're given a graph that looks smooth, we're assuming that no amount of zooming in will introduce some odd behavior like an oscillation. Okay, so limit as x approaches 0, what we have is I need x to approach 0 from the left and from the right. And although it's a hole there, both the left and the right values do approach 2. Okay, so again, remember that I don't need to have a point in order to have a limit at that point. Okay, limit is all about approaching, not about arriving. Next up, limit as x approaches 1, we already know does not exist from the previous calculations. And my last one here is limit as x approaches 3. So what do I have? 3 on the left, it approaches 0. And on the right, it will approach 1. So this limit too does not exist because the left-hand side limit and the right-hand side limit are actually different. Now let's take a look at the exact same function, but 2 limits that look quite a bit more complicated. So the key here is not to start doing math in scary quotes, okay? So math in scary quotes means that you're trying to apply some sort of arithmetic or massage this somehow or whatnot. The problem is there's nothing we can do about this because we don't know what the function f is as a formula. And algebraically, we can only work with formulas. So don't start trying to open up the brackets here. This is not f of 2 plus f of h. This is like definitely not the case. In fact, there's nothing at all we can do with the function f because all we have for it is a graph. And therefore, we must justify what these limits are from the graph and graph alone. Now, thinking about the graph and thinking also about this particular shape of an expression, does this ring any bells whatsoever? Does this look like something we have seen before? Forget the limit, forget the graph, just think about the general form of this exact expression. Have we seen something like this before? Pause the video and dig through the corridors of your mind to discover whether or not you can find this treasure of an expression in there somewhere. Hopefully, you actually did manage to remember that what this is f prime of x, the definition of the derivative of x. So what we had is this is equal to limit as h goes to 0 of f of x plus h minus f of x divided by h. So what I can see, I can simply literally just match this expression to this one. I can see that what's in the limit is identical. I can see these h's here are replicated by these h's here. This is quite literally a matching game. And the only thing that is different is that in my expression here, I have x's, and in my expression here, I have 2's, which means that this is just a derivative at 2, not at x, but at a very specific value for x, which is 2. Now, so far, this is not particularly helpful because I have no idea how to take derivatives. And even if I knew how to take derivatives from a formula, I don't have a formula. I have a graph. So what does the derivative represent on the graph? Pause, dig through your mind. What is the definition of derivative or instantaneous rate of change graphically? Graphically, this is a slope of tangent line to my graph at point x, which means that for my first question here, this is simply the slope of tangent line at the point x equals 2, right? Because my value for x here has actually been determined for me. And that, of course, is the information I can easily read off of the graph. So I need to construct myself a tangent line at x equals 2 and then figure out what the slope is. So at x equals 2, I'm at this point right here. I can see that my tangent line is going to look like this, and the slope of a horizontal line is equal to 0. Excellent, which means that the answer to this question is 0. That's it. There's no math, quote unquote. There is nothing to throw at this expression algebraically. All you have to do is reason it out. It is the most beautiful type of application of the actual math justifications because all we're really doing is thinking about what a derivative is and what it means on the graph. Similarly, the second equation here, right? Playing the exact same game, I already know that this expression looks like the derivative expression. So now we just have to figure out what value of x was plugged in here in order for it to work. Pause for a second and try to match this to find out what value of x this derivative is calculated at. Okay, this shouldn't take very long for you to notice that this is going to be the derivative at 0. If I set x to be 0 here, I'm going to get exactly the expression here, which means that once again, this is a slope of the tangent line to my graph at the point x equals 0. And now I just need to go to my graph and think about what happens in terms of tangent lines at x equals 0. Okay, so in terms of tangent lines at 0, here's my 0 here, so I'm drawing tangent lines here. Well, there's a couple of issues. First of all, there's no point to attach a tangent line to, right? In order for me to draw a tangent line, I have to actually put it on to a point, and there's a hole there. I can draw a tangent line attached to a hole. That won't be a tangent line. It will not be touching my graph. That's one issue. The second issue is even if this was filled in, so it's not really an issue, it's just more of if this wasn't a hole, I would still have a problem because tangent lines coming from the left will have a positive slope and tangent lines coming from the right would have a negative slope. Not knowing which one of them to take, I cannot take either. Okay, so whether this is a hole, which is the case here, or if this was actually filled in either scenario, I cannot draw a tangent line right here, which means that the limit that is actually the derivative at this point simply does not exist. Okay? Spend some time simply looking at this slide and realizing that just because you have an algebraic expression doesn't mean that you have to approach it algebraically. If the function is given to you as a graph, you have to resort to a graphical interpretation of the corresponding concepts. Now let's take a look at sort of the backwards idea. What I have here is a bunch of information about a function, but not a graph. And what I want to do is to create a possible graph of a function. Now, the actual qualities of the function that we're given here are not going to define a very unique shape. So the function that I will produce might be slightly different from the one you are producing or your friend is producing. Just make sure that as you draw it along, you actually check off and satisfy all of these properties. Okay, pause, take a second here and draw an example of a graph that satisfies these properties, and then draw another one that satisfies these properties. Okay, so let's say I am going to have a go at it. First, it's probably a good idea to see what kind of scale I need. So I can see that my x's are going to be 0 and 2. So this is as far in terms of x's I'm going to go. And my y's are going to be 2, -1, and 1. Okay, so my scale vertically is going to have to be somewhere between -1 and 2. And my scale horizontally only really needs to go between 0 and 2. Okay, so let's say 0, 1, 2, -1, 1, 2. Okay, don't start drawing the graph before you actually take a look at your information. What if this was like 100 and you started drawing the graph with the scale of 1? That will take you forever to fill it out, right? So my first piece of information is that as x approaches 0 from the left, my function approaches 2. So my function approaching 2 has to come from the left of the 0. Now I have no idea yet what happens at 0, so I'm just going to leave it be. As it approaches 0 from the right, it approaches -1. So 0 from the right approaches -1. I have to do something like this. Okay, now notice again, I haven't actually done anything here and I will have to decide what happens there. But the next one is helpful. F of 0 is not defined, which means that I cannot have a value of a function at 0, so I can't actually define it at either of those ends of those limits. Next, I am told that f of 2 is -1, so f of 2 has to exist at this point right here. And I'm also told that the limit as x approaches 2 actually does exist and is equal to 1, so up here. So the limit has to somehow end up there, but I can't have a function defined at 2 different points. So I can't plop a point here. This will have to be an actual hole. And the limit of my function has to actually approach this from the left and from the right. So I can have something like this, and let's say like this, okay? These examples, when you are asked to sketch a graph, you might need to erase what you've created and redo parts of it, because as you go along, you might discover properties that contradict the sketch that you've already produced, right? So for example, if I had decided that at this stage or at somewhere with the limit stage, I'm going to go up here and then, maybe continue increasing forever and forget to put in the hole, I will have to erase my graph in one spot and actually introduce a hole. Don't be scared about erasing. It's all about making sure that at the end, you've satisfied all the properties correctly, okay? So another checkpoint is once you think going one step at a time that you've produced a reasonable sketch, go through all of the actual properties again and make sure that your function satisfies them all. Now, what happens for this next one here? What I have in terms of my x scale is 0, 1, and 2. So I know that I can do something similar to that. What I have in terms of my y scale, though, it goes all the way up to 4. So I'm going to have to be a little bit more mindful of the fact that my graph is a little bit more vertically present, let's say, right? So my x's are 0, 1, and 2, and my y's 1, 2, 3, 4. Now, different people develop different approaches to these types of problems. Sometimes it's easier to plot the things that you know are on the graph. So for example, the exact points that there are. So f of 0 is 1, which means that I can plop this value right here. I know it has to be there, and I can sort of check this off. And f of 2 is 4, so I know that this value is also here. Now, f of 1 is not defined. That can be either a whole or it can be an asymptote. So if you really want, you can put in a hole there, but the problem is you're going to have to put holes everywhere. If you want to create an asymptote, we're really going to have to think about how the graph goes first. So maybe let's take a look at the limits first. So what I have is limit as x approaches 0 from the left and from the right is equal to 2, which means that around 0, the function is actually going to approach 2, which has to be an open circle because the function is defined at 1. But it will actually approach 2 from the left and from the right? So whichever way it decides to approach it here, let me create a little tail there. Okay, so it seems that I've satisfied these properties, but I also, again, remember that f of 1 is not defined, so I have to figure out what to do there. So let's say I can create a hole at 1. So my function maybe can sort of keep going, but at 1, I will have a hole, or I could create, alternatively, can keep going, but it will create an asymptote at 1. So something like this, right? So that can be checked off by either one of my graphs here. And finally, I have that the limit at 2 does not exist. So while the function is defined at 2, the limit there does not exist. So maybe I extend it and have a hole here at 2, and then have my function not go on the right-hand side. Okay, so that way, on the left of 2, it approaches whatever value this is, but on the right of 2, there is no function to talk about whatsoever. So altogether, my limit will not exist. So it doesn't matter which graph you pick. Let's say I pick my asymptotic looking one, and that should give me all my check marks throughout. Okay, once again, once you have your final sketch, go through and make sure you haven't somehow ruined one of the earlier properties that you've drawn by adjusting for your later ones.